First, I want to thanks organizer for. Let me see. Maybe I can. I want to thanks organizer, especially Anton, for kind invitation. I will speak on my topic. This one review paper about Osserman manifolds and duality principle. So how I can move?
We opened your file.
Okay. I can move with my.
So if it's not acceptable for you, then you'll have to open. Oh, как быть?
Aha. You open my. So may I share?
Maybe we stop our and you share your screen.
Okay, this is better.
Can you now change something?
Let me see.
Can you now scroll your text and?
Now I can. Okay.
You can. Okay.
Okay, it's okay then. So let's consider one pseudo-Riemannian manifold denoted by M. It's Levi-Civita connection, and it's not work so good. Okay, maybe I can. And then it's Riemannian curvature tensor which satisfies standard symmetries. Then it's well-defined Jacobi operator by that formula, this one. It is self-adjoint symmetric endomorphism of tangent bundle of manifold M. And in the Riemannian case, if M is flat of rank 1 symmetric space, then local isometries on M act transitively on the unit sphere bundle, and thus the eigenvalues of Jacobi operator are constant on unit sphere bundle. Osserman in 80s wondered if the converse is also true. So globally, it means that the eigenvalues do not depend on the point of manifold and on the unit vector X. Osserman manifolds necessarily flat or locally isometric to a rank 1 symmetric space. Osserman conjectures have been starting point for investigation of manifolds based on properties of spectra of natural operators defined by Riemannian curvature tensor. First, there were introduced some notions considered to this question. First, we say that the manifold is pointwise Osserman if the eigenvalues of Jacobi operators do not depend on the unit vector for every point P. So eigenvalues may vary from point to point. But if we fix one point, then for all unit vectors, it is constant. The natural approach to the Osserman conjecture was suggested by Gilkey, Swan, Ivan Hecke in their paper is from '94, I think. So this approach has two steps. First one is using the pointwise Osserman condition, find the algebraic curvature tensors at the point P, and so possible existence of additional algebraic structure. They found in the Riemannian case Clifford structure, and between those tensors which are constructed in the point 1, find only those algebraic curvature tensors which may be realized as curvature tensors of a Riemannian manifold. Notions of pointwise and globally Osserman conditions are not equivalent, for example, in dimension 4. For example, for compact K3 surfaces, quaternion Kähler orbit folds, local with non-zero scalar curvature, hyper-Kähler examples, and others. And now when we are in pseudo settings, so non-Riemannian, then we can consider pseudospheres or pseudosphere bundles of space-like and time-like vectors. And we say that M is globally space-like, time-like, or null. Osserman, if the characteristic polynomial of Jacobi operator is constant on sphere of space-like sphere bundle or time-like or null cone. M is space-like, time-like, or null Jordan Osserman if the Jordan normal form of R of X is constant when X belongs to unit time-like, space-like, or null cone. It was shown that the notions of globally space-like Osserman and globally time-like Osserman are the same, but the notions of globally space-like Jordan Osserman and globally time-like Jordan Osserman are inequivalent. Those results are proved maybe at the beginning of this century, more or less. Now we saw that. And that first, in the first step, very important is algebraic curvature tensors. So if we take finite dimensional real vector space, which is equipped with a non-degenerate symmetric bilinear form of signature PQ, then we can consider tensors of order 4 on this space. And if such tensor satisfies well-known symmetries as curvature tensor of Riemannian manifolds, then we say that is algebraic curvature tensor on V. We have, in considering manifolds, we have such situation in every point. One says that R is Osserman or Jordan Osserman algebraic curvature tensor if the associated Jacobi operator has characteristic polynomial or Jordan form constant of the unit spheres S minus and S plus. A pseudo-Riemannian manifold, in this part. So now we have this connection between point 1 and 2 in our approach. A pseudo-Riemannian manifold M is said to be geometric realization of R at the point P of some manifold if there exists an isometry from C from tangent space in the point P to V such that for all tangent vectors x, y, z, and w in tangent space, we have those two relations. Of course, it means that this is isometry. Here we denote by RP tilde curvature tensor of M restricted to point P from manifold. Gilkey showed that every algebraic curvature tensor on a vector space V of signature PQ is geometrically realizable. So this result enables us to work first in algebraic settings. It means to define a model and work in this model and later pass to the geometrical context. Then we have one interesting result by Fiedler and Gilkey. So the spanning set of the vector space of algebraic curvature tensor CV are two spaces. First one is that one which is characterized by symmetric endomorphism of V. This means SV. And A of V is antisymmetric, skew-symmetric endomorphism. And those two tensors are given by these formulas. So first one looks very close, looks like a tensor of constant sexual curvature, and second one is connected with some complex, almost complex structure. More precisely, this result means the following. So if we take arbitrary algebraic curvature tensor, then there exist two sets, one in which are some symmetric endomorphism, and another one consists of skew-symmetric endomorphism of V, such that we can represent our algebraic curvature tensor as a final sum of symmetric or skew-symmetric endomorphism, where this epsilon psi I or epsilon theta j are 1 or -1, and this signs could not be changed if we have fixed some fixed algebraic curvature tensor. One of the most important tool in the reconstruction of algebraic curvature tensor of a pointwise Osserman manifold is duality principle. This principle says following. This is property of Jacobi operator or of curvature. So if we have eigenvalue lambda of Jacobi operator, and if x and y are unit vectors, then if lambda is eigenvalue of Jacobi operator Rx for the vector y, then we can interchange roles of vectors, unit vectors x and y. So it means this is true if and only if x is eigenvalue of Jacobi operator R of y for eigenvalue lambda. Later, this was as it's written here. It is considered a Riemannian case, and then with my student Vladica Andreji, we extend this notion to arbitrary definite vectors. It means vectors which length is not zero. So it means it could be space-like or time-like. And we proved the following theorem. So if M be a diagonalizable Osserman pseudo-Riemannian manifold, then if there is no null eigenvector of Jacobi operator for all definite vectors x, then M satisfies duality principle. M satisfies the duality principle in the case where R or Fx has all different eigenvalues. And if M is four-dimensional manifold, then duality principle holds in any signature. We wanted also to extend our definition to the null case. It means that if we take non-zero null vectors x and y, we say that they are totally dual if the following equivalence holds. So it means if y is element of eigenspace of Jacobi operator R of x, then x is eigenvector of R of y. So this definition is more general because here it is allowed that x and y could be any vectors different from zero, from zero vectors. It could be null vectors. Then now I will give some things which shows, since it is clear more or less from definition that we can reformulate Osserman condition using K-Stein, notion of K-Stein. So we say that algebraic curvature tensor is K-Stein if there exists constants say j for j from j from 1 to k such that a trace of I power of Jacobi operator is proportional to the norm of it is proportional to the norm of vector x with the eigenvalue 2 times e. And then if R be an algebraic curvature tensor on vector space V of signature PQ, the following conditions are equivalent and define the notion of K-Stein algebraic tensor. So this result is due to Professor Gilkey, his monography about natural operators defined by curvature by curvature of manifold or by curvature tensor. So it means if P is greater than 1, the following conditions are equivalent and define the notion of K-Stein algebraic curvature tensor. For if P is greater than 1, then a trace of a Jacobi operator to the ith power is constant on unit time-like vectors for all I between 1 and k. Similar if Q is greater than 1 and trace of the same trace of Jacobi of the power of Jacobi operator is constant on time-like on space-like vector, and there exists constant Ci such that trace of Jacobi operator is K-Stein. So it is enough to check first or two. Proposition 4 shows in the case when k is equal to n that the notions of time-like Osserman algebraic curvature tensor, space-like Osserman algebraic curvature tensor, and Einstein algebraic curvature tensor are equivalent. And also from this book we have the following proposition: if R be an algebraic curvature tensor on a vector space V of signature PQ, when Q is greater than 2, then if X is non-trivial null vector of V, if R is Einstein, then A of X is the Jacobi operator of that vector, null vector is nilpotent. The following result discover four-dimensional Osserman manifolds. If let M be four-dimensional pseudo-Riemannian manifold, then the following statements are equivalent. M is pointwise Osserman. There is a choice of orientation of M such that it is Einstein self-dual or Einstein and anti-self-dual manifold. First result for the Riemannian case is proved by Gilkey, Swan, and Van Hecke. And in all other cases, it means basically in the case 2-2 signature is proved by Nikolayevsky, Bokan, Blažić, and myself. So now we will say something about the Riemannian case, Osserman conjecture Riemannian case. As it is known that Adam's number are defined as follows. So mu1 is 0, mu2 is 1, mu4 is 3, mu8 is 7, and then we have these recurrent relations. Mu 16 times m is mu of m plus 8, and this one for other cases. And then those numbers are related with non-trivial decomposition of the tangent bundle of unit sphere. And we have this very famous theorem given by Adams So suppose that we have non-trivial decomposition of tangent bundle in as an orthogonal direct sum of vector bundles on dimensions ni I, where ni zero, when these dimensions are given in this order, so ni zero is the biggest and or other dimension less than previous one. And if then sum all dimension except this first one is less or equal to Adam's number of k. K is number of this vector spaces F0, F of these vector bundles. Special this very strong theorem which could be applied in Riemannian case, since it is true for Riemannian. In the Riemannian case, especially it implies if M is equal 1, it means if dimension is odd, that Jacobi operator, restricted the Jacobi operator has only one eigenvalue. Restricted means that we exclude from M line, from V line X on one-dimensional, because X is always eigenvalue of Jacobi operator R of X. It is not important. And in case when the dimension is divided by 2 but not by 4, then restricted Jacobi operator has at most 2 eigenvalues. And especially if R of X, this restricted operator has 2 distinct eigenvalues, then one eigenvalue has multiplicity 1 and no other, and another is rest. It means very big dimension. And then also Gilkey, Swan, and Van Hecke in this paper mentioned they considered the real Clifford module structure. So it is collection of linear maps of almost complex structure which anti-commute, and they proved the following in Riemannian case. If we have a Clifford module structure on R of n and consider a set of generators, these linear maps, and if lambda 0, lambda 1, lambda nu are arbitrarily real numbers, then we have this decomposition of algebraic curvature tensor. First part, it means this one, this part, first one belongs to, it is curvature tensor of the space of constant sectional curvature. It is given by this formula, and the last rest of them are those which belongs to this almost complex structures. So it is this connected with the theorem about generators of a space of algebraic curvature tensor. This result given by Fiedler and Gilkey. And this tensor is Osserman algebraic curvature tensor with this formula. So here we see that for Jacobi operator of X, J, I, X are eigenvectors with these given eigenvalues. They are non-null unit vectors, and Y is orthogonal to this span of space spanned by X and the action of almost complex structures J1 to J nu to X. And in Riemannian's case, Osserman conjecture is proved in all cases except in dimension. In some cases, depending on the structure of eigenvalues in dimension m equal to 16 due to work of Nikolayevsky, and she proved the theorem for m not equal to 4 times k and k greater than 1. In Lorentzian case, Osserman conjecture holds due to this result given by Blažić, Bokan, and Gilkey. So if R be a two-stan algebraic curvature tensor on vector space of Lorentzian signature, then R has a constant sectional curvature. Especially if let M be pointwise Lorentzian Osserman manifolds, then it has constant sectional curvature and consequently Osserman conjecture holds. So in the next dimension by complexity is manifold of dimension 4 in signature 2, 2. But in this case, we have this theorem which describes all possibilities for symmetric operator on such space. We have 4 cases. First one, in first one we have that all eigenvalues are real. In second one we have one complex root of minimal polynomial. It means also characteristic polynomial. Then we have case 2. So this 1b is for complex. 2 is if we have alpha is the double root of minimal polynomial, and case 3 is when alpha is triple root. Let me see. And then using previous decomposition, we proved the following theorem, Blažić, Bokan, and myself. So let M be 4-dimensional pseudo-Riemannian manifold of signature 2, then the following statements are equivalent. M is time like Osserman, M is space like Osserman. The universal covering space M tilde of M is one of the following manifolds. M tilde is a manifold of constant sectional curvature, M tilde is scalar manifold of constant holomorphic sectional curvature, and M tilde is para-complex manifold of constant para-holomorphic sectional curvature. Those three cases corresponds to diagonalizable Jacobi operator, and the last one, the Jacobi operator of M tilde is non-diagonalizable. Its characteristic polynomial either has a triple zero alpha or a double root alpha and one root which is equal beta. Beta is equal 4 times alpha, or beta equal to alpha, and this curvature is given by the following lemma.
Professor Rakic,
yes.
I'm afraid you have just a couple of minutes left.
Okay, so we will finish, and don't worry. I hope. So here I will skip something since so this lemma gives as you see in this it is mentioned in previous theorem. So if we have double root, if Jacobi operator has double root alpha, then we have only those 5 non-valency component of R, and similarly in the case when we have triple root alpha, then we have 6 non-valency component. And then I constructed example of manifold of dimension 4, which is time-like Osserman, rank 2 homogeneous symmetric space, and this was the first example which shows that Osserman conjecture doesn't hold in pseudo-Riemannian case, a similar result is obtained by Garcia, Rio, and Cupelli. He constructed this this manifold, which has also some additional properties. I will skip this since I don't have. So maybe I can mention this. So we obtained also in our this paper that in case of four-dimensional Jordan-Osserman pseudo-Riemannian manifold of signature 2, 2 of type 2 or 3, then we can find the coordinate system where matrix is given by this G with these zeros here. Such metrics are called Walker metrics. And after that, they became popular. Gilkey and his co-author wrote one interesting monography on this spaces. So here we will skip this, and here we can give this conclusion. Osserman conjecture holds in Lorentzian manifolds. Osserman conjecture holds in Riemannian manifolds up to few cases in dimension 16. Manifolds of signature PQ, where smaller number of P and Q is greater than 2 or equal. Conjecture doesn't hold. Geometry of such manifold is very rich, especially in neutral signature. Now we are very far of complete description of geometry of such manifolds. So only I can say if you give me just 2 minutes. So here we have in this part we can show that duality principle is equivalent with the Osserman condition. First, it was proved in pointwise Osserman condition in small dimensions by Brozus, Vasquez, and Merino. And then by Yury, Nikolayevsky, and me, we proved that Osserman condition equivalent to duality principle in Riemannian signature. So this is this result. It can be a little bit extended to pseudo-Riemannian cases and diagonalizable Jacobi operator, and on some complexification. So by Andreji, we show that a Clifford algebraic curvature tensor satisfies duality principle in many signatures. And let R be totally dual algebraic curvature tensor on the vector space of signature 1 n, then is real space 4. We have these examples of totally dual manifolds. And this is the last counter example, is this metric, which is a Walker metric, which shows that from that metric we can conclude that characteristic and minimal polynomials are lambda to the fourth and lambda to the third. Is global Jordan-Osserman manifold, and direct calculations gives these two relations. First one shows that that partial derivative with respect to x1 is this vector fields is eigen in the eigenvalue is eigenvector of R of this vector space delta over delta x3, and in second formula shows that if we replace roles of these vector fields, then we obtained a formula which shows that vector field for delta over delta x3 is not eigenvector. So it means it shows that this pseudo-Riemannian manifold is Osserman and Jordan-Osserman, but it's not totally dual. So this is the whole. Thanks for understanding, and I'm sorry because of lating.
No, that's okay. Thank you very much for your talk. Are there questions? You made a very big survey, but could you show the slide with this duality?
The last one or at the beginning?
In the
So
beginning.
let me try to. It doesn't work. I could not.
No, you can налево направо, да?
Okay, now it so let me see. We have here, it's not, okay, yeah, it is here. Here is, so this is algebraic curvature tensors. We have some time. It is not here, so this is this one. So we show that this duality is equivalent to, it's more a simple condition than this condition given by Osserman in his definition. So since it's this duality principle is easier, it's more, you don't you need it's easier to understand this.
So it's duality for these Jacobi operators, and you apply it to manifolds.
Yes.
Okay. More questions? Maybe if someone has, can write an email.
Of course.
And yes, thank you very much for this.
Thank you. Also,
survey. Yes, thank you very much.
Okay, thank you.
Yeah. Bye-bye. So we have a break, and